Welcome to a late Friday afternoon Meow seminar by Sreejata. Oh, great. And he'll tell us about Aaronson and Ambainis conjecture. Well, it's section two.
Thanks for the introduction. So I'm going to start by describing a math problem. And we'll see how it comes around. So this problem was inspired by trying to simulate quantum query algorithms classically. But in the end, this problem has nothing to do with quantum algorithms. So I'll just state the problem here. So So here's the problem. You're given a polynomial that maps the Boolean hypercube to the bounded interval 0, 1, and the degree of the polynomial is at most d. Then for any epsilon greater than 0, there's a decision tree of the at most polynomial in d and 1 by epsilon, which approximates your polynomial in the L2 norm up to error epsilon. And for people who aren't familiar with this notation, L2 norm is the expected difference squared. And unless I specify otherwise, all expectations probabilities will be over the uniform distribution over the hypercube. And it's a very simple problem. You are given a low degree polynomial whose image is bounded. You want to approximate it by making classically, you want to approximate it by classically making a small number of queries. And this is a big open problem in the literature. If you can solve it, you'll become very famous. So I'll start by describing some motivation behind this problem. So the story goes like this. So after quantum algorithms are discovered, people try to figure out situations where quantum algorithms are provably faster than classical algorithms. So the most famous example of this is Shor's algorithm, and another example is Grover's algorithm. And for this talk, we'll only be considering situations where the speedup is super polynomial. So we want to come up with some task such that a classical algorithm takes far longer time to solve it than a quantum algorithm, whereby far longer, I mean it's not bounded by any polynomial function. So one such conjectured task is factoring large numbers. This is, of course, it's well known quantum algorithms can solve this very quick. But the thing is, we don't provably know classical algorithms cannot factor large numbers. There's no algorithm known, but if you want to show that factoring is hard for classical algorithms, you will have to solve P not equal to NP, among other things, so something much more. And this is a general situation because if you want to provably find some task that that quantum computers are far better than classical computers, you'll have to prove some lower bounds for classical computers. And in this, as we all know, is a very hard task. So a bit more formally, quantum algorithms, the complexity class of tasks solvable by quantum algorithms is known as BQP. And it's known that BQP is contained in P space. Now, if your goal is to come up with some task which classical computers cannot do, but quantum computers can do, you will have to essentially separate P with P from P space. And this is an impossible task. So we give up on this. Now, instead, we switch to the Oracle model. So in the Oracle model, you have some input. Basically, what I'm trying to say is we switch to a model where we can prove classical lower bounds and then see what happens. So in the Oracle model, there is some input X, but you don't know what X is. You are, suppose this is U, and you are trying to compute f of X. But the point is, you don't know what X is. And you are a computationally unbounded person. You can solve the Halting problem if you want, but you don't know what the input is. Now, in the classical model, the way these things works is there is some person who has this entire input X, which is a string in plus minus 1 power n. And at any point of time, you can ask that person for the value of the I coordinate, and he will reply truthfully. And depending on the response you got, you issue another query, and so on and so forth until you know for sure what f of x is. And in between issuing two successive queries, you can do as many complicated computations as you want. You are not limited by that. You are limited only by the access to the input. So let's define the query complexity of f to be the worst case. In worst case, what's the number of queries you need to make to determine f of x? Let's call this the deterministic query complexity of f. You can also define a variant where you can use randomized strategies. So you have random coins at your disposal. And the variant we get is the randomized query complexity. Okay, let's call that R of f. And there's the third variant. This is the one we'll be concerned with. So you are a quantum computer and you can query X in superposition. So what do I mean by querying X in superposition? In this part, I'm going to assume a bit of quantum knowledge, but for the rest of the talk, this is not going to be very important. So if you don't follow the next 5 minutes, don't worry. But I'm going to define a model of what it means for a quantum computer to query input in superposition. So this means uh, so instead of the input being encoded as a binary string of length n, it's encoded as a unitary matrix, a unitary operator that applies on of size 2 power n plus 2 power n. And it's a diagonal matrix. Its action on the basis states is as follows. Sorry. It's a n cross n binary matrix. And its action on the basis states is as follows. So if you want to know the value of xj, you apply ux to the standard basis vector j, and it outputs the value as a phase applied to j. And querying superposition means you can apply ux to an arbitrary superposition of the basis vectors, and it will respond to the corresponding superposition. And the simulation and the quantum query algorithm does the following. So let's say this is the input for it. And this is the ancilla part. So a single quantum query looks like this. You start with some predefined state. Now there is some guy who has this unitary operator ux. So at one point of time, you say this guy to apply this unitary operator on the input part, and then you apply some arbitrary unitary to the entire ancilla plus input part. This unitary could be as complicated as you want, but it cannot depend on x since you do not know what x is. So this is one quantum query. So for the second quantum query, the same thing happens. The person who holds ux applies it to the input part, and then you apply another complicated unitary on the entire portion. The crucial point is these things do not depend on the input, and these things are you don't know what these things are doing. You know it's doing this thing, but you don't know what the phases exactly are. So you do this for at most q times. And in the end, what you will do is you will measure a qubit. And if you get the measurement to be 1, you output 1, otherwise you output 0. And this is a quantum query algorithm which makes at most q queries. And the first thing that someone might object is in a classical query algorithm, you are allowed to be adaptive. As in, you can query x1, then depending on what the value of x1 is, you can issue the next query. Here it seems like you are not making any intermediate measurements. You are just letting this guy operate ux. Then you do something, and this is going to be same across all your operations. You do regardless of what x is. So one might think this is a very limited non-adaptive measurement, but one funny fact about quantum query algorithms is that you can actually encode adaptive measurements here, as in uh, if you are doing something like you are measuring a qubit and depending on that output, you follow one branch, otherwise you follow one branch. There's an equivalent quantum query algorithm where there's a single branch and you manage it using a bunch of C0 gates. So this is our model of a quantum query algorithm. And it formalizes the intuition that a quantum computer can query the input in superposition. Okay, so that's it about quantum query algorithms, and we are not going to use this description later on. So if you don't care about quantum, I think you can understand the rest of the talk.
Just one question about the model. So you could also complain maybe that a classic decision tree only looks at one bit at a time. And here, if I understand correctly, you're somehow quantumly accessing the whole input string in every query. And you'd say that seems unfair.
So that is the point. Quantum query algorithms can query in superposition, and that is the advantage we are going to exploit. So if you look at how the quantum query algorithm works, if it inputs any basis state to ux, it gets the corresponding superposition back. But right now, it cannot really get all the bits simultaneously. At each measurement still gives it only one bit of information. So while it can query everything in superposition, it has to use the constructive and destructive interference in a creative manner to get the information it wants in the end.
Okay, but can I say like you say clearly stronger than decision trees, classic decision trees? Like, is it stronger than a parity decision tree? Also, obviously, or like.
So okay, as there's a surprise that's going to come for total Boolean functions. This model does not offer any advantage over classical query algorithms. So even though it might look like it's doing some very powerful operations, unless your input is already promised to have some sort of structure, you really don't know if this extra power helps. And okay, it might feel unfair, but this is how quantum mechanics works. So when if two vectors are in your basis space, then any superposition is also in your basis space. So you're just modeling how physics works in real life in some sense.
Okay, thank you.
Cool. So yeah, as Jakob said, it might look unfair that the quantum query algorithm can like plug the uniform superposition over all basis vectors and get some global information. But then it has to process this global information in a creative manner to get the information it really wants. So here's a surprising fact. So let me just define Q of F first. So yeah, I'm going to say something surprising. That is for total Boolean functions, quantum queries don't give you any significant advantage over classical queries. But before that, let me just say that there are two types of situations that one can consider. So one can consider total functions and partial functions. In a total function, the function is defined everywhere on the Boolean hypercube, and you have to find the output on every point. And in a partial Boolean function, the function is defined only on a subset of the Boolean hypercube, and you only have to output the correct answer on the subset. You don't care what happens outside the promised set. So, okay, technically speaking, a total Boolean function is also a partial Boolean function where the subset is the entire hypercube. But roughly speaking, when we talk about partial Boolean functions, we talk about situations where the promised set is much smaller than the entire Boolean hypercube. So, let me just write this here. I have to delete something, so I will delete this. So there are two different situations which one can consider. Now it turns out for total Boolean function, it's known that quantum query algorithms do not give you any super polynomial advantage over classical query algorithms. So this is despite the fact what Jacob currently pointed out that the quantum algorithm can get some sort of global information at each query. It turns out this does not help when the function is Boolean. Total. Sorry.
Do you have a short explanation why?
Okay. I was about to start.
Sorry,
I was about to start explaining that. Yeah. All right. So this is some fact. So when it was first proven, we got the exponent 8. I think the current best known exponent is 2. This was a stock 21 paper by Aaronson-Ambainis. I don't remember if it's 2 or 2.5. So I'll just write 2.5 to be safe. Okay. So in case the function is total, you don't have any advantage unless you count these fine range distinctions. Now, what about partial Boolean functions? Now the story changes quite a bit. So for partial Boolean functions, there exist partial functions for which quantum query complexity is order 1, but classical query complexity is something like n square root n. Even randomized query complexity is square root n. So there's a stark difference between what happens when the function is total versus the function is partial. Is something wrong? Okay.
So about this result for total Boolean functions.
Yeah.
So why? Do you have a short explanation? Why?
Yeah, I'm coming to that, but I will just say tell you in two lines, and I'll elaborate later.
Okay. Sorry.
The acceptance probability of a quantum query algorithm can be approximated by a low degree polynomial. If it's a total function, the low degree polynomial is always between 0 and 1/3 or 2/3 or 1, depending on if fx is 0 or 1. And there's a classical result by Aaronson-Ambainis which says you can approximate such functions by a decision.
Okay.
That's it. And the Aaronson-Ambainis result is highly non-trivial, so that's it. Means yeah. And this gives you df power 8 to get it all the way down to 2 power 5. You need to do some spectral analysis on some weird matrices. It's a long line of work to get all the way down here.
What is the conjectured?
Yeah, I am coming to that. So for total functions, it's settled.
Okay.
For partial functions, like I said, the story is much more complicated because there can be functions such that the quantum query complexity is order 1 and the randomized classical query complexity is omega square root n. This is the correlation problem in case anyone wants to know. But here's the strange thing. For all such f where we know of a huge separation between quantum and classical query complexity, it turns out that this partial promise set is a exponentially small fraction of the Boolean hypercube. For example, for this problem that I just mentioned, so by mu I mean the probability the measure under the uniform distribution. So for this function I just mentioned, the measure of the promise set is exponentially small. And it turns out this is true for all examples that we know of. And essentially the reason why this happens is any situation where you want to get a super polynomial speed up, kind of the only thing you will do is quantum Fourier transform. And if you want the Fourier transform to give you some useful properties, you need some promise structure in the input. You need the input to have some sort of periodic structure. Like very roughly speaking, this is what happens. The promise set promises that the input has some periodic structure, and then you use quantum Fourier transform to extract that periodic structure out. But you do need this very structured and stringent promises. So now the question we're interested in is what happens when the promise set has no structure. So let's talk about this situation when so this is the situation. Let's ask what happens when the promise set is around half. So it's not defined everywhere, but it's defined on a large fraction of the hypercube. Can quantum query algorithms still be simulated by classical query algorithms? And this is the question we will be interested in. So I'm not going to write this down because I'm going to write down something else. But this is what we want. Let's say given a partial Boolean function whose promise set is a constant fraction of the Boolean hypercube, and given a quantum query algorithm that correctly computes x on everywhere on this promise set, can you find the equivalent classical decision tree with not too much depth that computes it everywhere, that predicts the behavior of the quantum query algorithm everywhere on this promise set? Well, it turns out for a very stupid reason, this isn't always possible because in a very small fraction of this S, this function could be hidden. So, I mean, I hope the audience is getting what I say. If given any such quantum query algorithm, you cannot really expect a classical query algorithm to be able to simulate its behavior on all S, because this S might include the promise set of this separating function. So now we ask the next possible question. Can we approximate the behavior of the quantum query algorithm on most of the set S? And let's kind of now forget that this quantum query algorithm was computing a partial Boolean function. This is what we want to ask. Okay, let's erase this. And this is the conjecture. Even any quantum query algorithm, you can simulate its behavior on most inputs by a classical decision tree, which does not make too many more queries. And if this conjecture is true, you can see that for the case when the quantum query algorithm is computing a partial Boolean function on a large fraction of the hypercube, you can predict its behavior on most portions of the hypercube by simply picking epsilon to be small enough so that by Markov's inequality, you can see even within this hypercube, you are not eroding too much. So this is the conjecture. This is a big conjecture in the literature.
So sorry, can you repeat this again with the measure of 1/2?
Okay, so I just deleted it.
What's
Sorry.
there? So
Yeah, okay, let's. So what I just said is that we know partial Boolean functions for which there is a wide separation between the classical and quantum query complexities. But it turns out that for all these cases, the measure of that promise set is exponentially small. Now we want to, so okay, we know if the promise set is the entire Boolean hypercube, we know there is no quantum advantage. We know there are cases where we get quantum advantage, but for that the measure of the promise set is exponentially small. What we have zero idea about is what happens when the measure is a constant. So it's not one, but it's a constant. Now, one might conjecture the following. Suppose the measure of the promise set is at least half or some constant. Then given a quantum query algorithm that computes the correct function on S, there's also a classical query algorithm that computes the same function at X. But this is kind of too much to expect because a small portion of your S might contain the promise set of this separating function. So instead we say, instead of simulating the behavior on most of S, we want all of S, we want it to simulate on most of S. And now we kind of forget that there was an S to begin with. This is what we conjectured. Let Q be a quantum query algorithm that makes at most Q queries. Okay, and so let Q be a quantum query algorithm that operates on n qubits. For every x, define this function that Q outputs 1 on x. Then for any epsilon greater than 0, you can find a classical decision tree which approximates P in the L2 norm up to error epsilon. Now, the distinction between total and partial function there comes in this way. Suppose suppose this is a quantum query algorithm to compute a total Boolean function. That means for any x, P of x is either between 0 and 1/3 or between 2/3 or 1, because that is how high acceptance probability is defined. So for those quantum query algorithms, you have this extra structure on P of x, which you can utilize to see if it's actually close to 0 or closer to 1. Now, in general, for a partial Boolean function whose promise set is S, you know that for points in S, this quantity is either very small or very large. But in between, it can do some random things. It cannot put half, it cannot put things arbitrarily close to half. You have no control over that. So now we kind of forget that there was a promise set to begin with. We're using this is some contemporary algorithm. It just exists. It's not trying to compute anything. It's just out there, and we are trying to simulate it. It might not be even computing a function. So computing a function at a point means that this probability is either less than 1/3 or more than 2/3. But this might not be the case for any input, or it might be the case for some inputs and not all inputs. We don't care. Let's say whatever this value is, we want to approximate it on most inputs, yeah, or on expectation. And the depth should not blow up by too much. And this is a very significant conjecture in quantum complexity. I hope I have given you sufficient motivation to study this. This also implies some oracle non-separation results with respect to a random oracle. This might be wrong. P power equals BQ P power or something like that. I don't remember that. No, sorry. But I hope I have provided sufficient motivation to study this conjecture. And now I'm going to say one magical fact about quantum query algorithms.
Question. So I don't know if we're spoiling some suspense here, but this is a conjecture. Is there any consensus on the likely status of this conjecture? Like everybody's like, this is of course P is distinct from NP, or like this is genuinely open, nobody knows.
The consensus is this is true. So I mean, from everyone I've spoken to, they say this is true. So I'm assuming the consensus is there. So this is true.
So, but then the idea would be that you can effectively always simulate quantum query algorithms like classical decision trees, so error and so on, according to this.
Yeah.
But then we would expect that if instead of doing query algorithms, you actually give the algorithm the input, their quantum algorithms will have an advantage.
Yeah.
That would be the expected help.
Yeah. So I would say another reason for the consensus is that with respect to a random oracle, we know that P equals BQP. So the input here plays the part of the oracle. Right. And expectation of X means we are like taking a random oracle. Like, okay, I don't know if you know, you think P power equals BQP power. Okay, I don't remember this right now, but for some complexity theoretic reasons, the consensus is this is believed to be true. And the point is, yeah, we are not trying to simulate the behavior on most points. On all points, we just want to simulate it on expectation. Now, of course, there will always be some error set depending on what epsilon you choose. And you don't have control over what error set there is, but you do have control over the fact that you can simulate its behavior on most inputs.
Okay, my question is that despite the fact that with respect to a quantum oracle, these three classes are different,
yeah.
we expect that without an oracle, P is different.
Yeah. And the entire point of going to the oracle model is we cannot really prove lower bounds in the first place. And then we're just studying what happens in the oracle model. So if you look at worst case oracles, we know there are situations like this, but here we're looking at an average case. Right. So, and now I'm going to state one magical fact about quantum query algorithms. Let's say it makes at most key queries. I forgot to mention this. And here is a very well-known fact. So if the quantum query algorithm makes at most q queries, the degree of the acceptance probability function is at most twice the number of queries. And this is the thing that we're going to use in the rest of the analysis. And to recap what Kilian had asked, this is the fact that gives you how to classically simulate quantum query algorithms. Because if you have a quantum query algorithm that computes a total Boolean function and makes at most q queries, then you have a function whose degree is at most 2q, and at every point in the Boolean hypercube, it's bounded away from half. It's either less than 1/3 or more than 2/3. And there is a seminal result by Nissan and Szegedy using things like block sensitivity, which show that there exist classical decision trees for such functions whose depth is at most polynomial in the degree. And that's the result. The issue here is that Nissan-Szegedy is kind of a very non-robust argument. It says that if your function value is bounded away from half at every point, then you cannot, then you can find a classical decision tree that computes it at every point. But even if it happens that your function is bounded away from half on most points, but on some in a small number of points it's close to half. Even in this situation, we don't know how to construct a classical decision tree which only approximates it on the points that it's far away from half one. So Nissan-Szegedy is not a very robust argument, which is why just from this we cannot get anything here. So we need something more. And what researchers suggested is we forget the fact that P is arriving from some classical query algorithm. We just use the fact that the value of P lies between 0 and 1 everywhere, and its degree is bounded. And now we try to classically estimate it on most points using a classical decision tree. So this is the conjecture that I mentioned in the beginning.
Do you lose anything if you make this assumption? Like, is the other way around also true?
No, not all. It's not true that all polynomials arise, all low-degree polynomials arise from low quantum algorithms. There is more structure to quantum query these polynomials. There's something called completely bounded block multilinear forms. So people have even tried using this structure to try to get something more. But it's kind of very messy. I will not go into that here. But there's a line of research which says let's try to use the additional structure that P has to prove something more.
So the conjecture is harder than just.
Yeah, the conjecture is harder. But if you want to get famous, even this will be good enough. So.
And here it is, well, you wrote it, I guess, but it's important that we are over plus minus one here, I guess. For instance, so the parity now has a high, like if I'm mapping parity from plus minus one to 0, 1, then this will have a high degree.
Yeah, I know the plus minus one I'm doing just because I can do Fourier analysis here. But so parity, the quantum query complexity for parity is order n. So this should not really tell you anything.
No, but parity in the 0, 1 basis would like have would be a very low degree polynomial, right? Getting back to your original conjecture. There it would like parity would have been a problematic example for you, but not over plus minus 1.
So let's try to, so by parity even in 0, 1 power n is high. If you're talking about in as a function from f2 power n to f2, like it's f2 degree, then no. But if you're talking about its De Morgan representation, as in 0, 1 power n to 0 power 1 over the reals, then parity's degree remains high. Right?
Okay. Mm-hmm.
As in, I mean, you are probably saying the f2 degree of parity is small. Yeah,
yes,
that's true. But here we're not talking about the f2 degree, we're talking about the real degree. So the degree does not change if you shift from plus minus 1 to 0, 0, 1 if you stay in the reals. Yeah. Right? So I hope you agree with this.
Just doing the linear transform.
Yeah, just doing a linear transformation. It does not change the degree. An invertible linear transformation. Yeah, if f2 degree is not relevant for this talk. But so I think I should just clarify degree here means degree over the reals. And the domain does not matter because there's always between any two domains there's an invertible linear transformation taking one domain to the other. So the degree remains the same. The reason I chose plus minus 1 power n as the domain here because it helps me to do Fourier analysis. So I'll continue if that's okay.
Mm-hmm.
Yeah. Okay. So, like I said, a line of research focused on the following direction. We forget the fact that P of X arises from a quantum query algorithm and instead try to approximate any low degree function instead. And this gives rise to the original conjecture. Do I have to write this again or I hope people remember it? Yeah, I hope people remember it. Given any low degree function, you can approximate it by a classical query algorithm whose depth is polynomial in the degree of the function. And And the next line of work I'm going to focus on is the Aaronson-Ambainis conjecture. So in 2014, I think it was a bit before that, Aaronson and Ambainis gave a recipe to construct a classical decision tree out of any low degree polynomial. And they gave a mathematical conjecture such that if the conjecture is true, then their classical decision tree works. And so I'm going to describe their procedure of constructing this classical decision tree now. So we have a low degree function. Now there will be two quantities that are important for us. We first define variance of P. This is just a variance of the random variable P of X when X is sampled uniformly at random. And we'll need the notion of the inference of a coordinate. So the inference of the ith coordinate is a measure of the following quantity. You sample a point uniformly at random, then you flip the ith coordinate, and then you take the difference and take the square of that difference, and you see by how much this difference, how big this difference is. You scale down by 4 so that some Fourier analytic expressions look nice. So these are the two quantities that we need. Now note that if the variance of P is small, then we don't need to query anything. We can just output the mean of X. And just by the definition of the variance, we know that is a good approximation. Now, Aaronson and Ambainis suggested the following query algorithm. So, this is your polynomial. So suppose the variance of your polynomial is small, then you're done already. You don't need to do anything, just output its mean. If the variance of the polynomial is high, you instead find a coordinate I which has the largest influence. So you query that coordinate. Now, based on the output, you move to a restriction of P. Because, for example, if you query xi, then you get xi equals to 1. Now, the polynomial you have is P restricted to xi equals to 1. Now, you do the same thing. If the variance of this restricted polynomial is small, you just output its mean. Otherwise, you take its most influential coordinate and query it. And keep doing this until the variance drops down. So, one thing that's clear is when this algorithm terminates, the variance has dropped down. So this is an accurate approximation of P. The thing that is not clear is why does this algorithm terminate in a small number of steps? And so Aaronson and Ambainis came up with this conjecture. So if this conjecture is true, then we can show that this query algorithm will terminate in a small number of steps. And this is the Aaronson-Ambainis conjecture. It states that if the variance of your polynomial is high, okay, I should replace this one. So it states that if the variance of the polynomial is high and it has low degree, then there is a coordinate whose influence is very high. And the query algorithm then at each point of time, as long as the variance of the polynomial is high, it locates an influential coordinate whose influence is at least this much, queries it, moves down, and does the same thing until until the total variance has gone down.
D is the degree, or
D is the degree. Yeah. So I think for the first half of this talk, I'll give a brief proof sketch of why the Aaronson-Ambainis conjecture implies a classical simulation of this classical simulation works. So, okay. So I think I will finish the first half after I show this simulation result. So let's call this the AA conjecture because it's shorter to write. Right. So let's quickly see why this works. So the query algorithm works in the following manner. You have P here. Let's say we are trying to get an accuracy of epsilon. So the variance, let's assume the variance of P is at least epsilon. Because if not, you can just output the mean and you are done. Now, since the variance of P is at least epsilon, and we are assuming this conjecture is true, there is a I whose influence is at least polynomial in variance and 1 by d. So let's query this line. Now, depending on what value we got, we get two possible restrictions. If we get xi is 1, then we move to the restriction p restricted to xi equals to 1. And similarly for the other thing. Now the main thing we want to show is the following. Since I had high influence, after this query, on expectation, the variance of these two polynomials drops down. So we'll show that, and so let's compute. So if we get xi equals to 1, the variance becomes the variance of this restriction. If xi equals -1, the variance of the polynomial becomes the variance of this restriction. So let's try to compute what the average variance of these two polynomials is. So if you unwind the definitions of influence and yes.
Yeah, can I ask? So the Aaronson conjecture,
Yeah.
the AA conjecture. So does this hold for any d or just for constant d or small d?
For constant d, it's known to be true.
Oh, okay. So but the conjecture holds for d up to n.
It's conjectured to hold for d up to n.
Okay.
But you can show that the max influence is at least 1 by n times variance. So if d is at least polynomial, like n power 1 by 100, if d is above that threshold, it's automatically true.
Okay.
So kind of the interesting regime here is when d is around log n to polylog n. This reason will become clear in the second half.
Okay.
Right. So okay, let's see how this simulation works. So after you query p, on expectation, the variance of your next function becomes this quantity. And if you unwind the definitions and see what's going on, expand everything, there's a much easier way to see this using Fourier analysis. But you can see this is equals to the original variance minus the ith influence. Right. So what has happened here is initially your influence variance was large. In these two branches, the average variance has dropped down significantly since the influence of the coordinate that you queried was high. And I'm going to use one more fact about analysis of bounded functions. The influence of a bounded function is always upper bounded by its degree. And the variance of a function, okay, let me have to define something, I guess. Let's define the influence of a function to be the total influence. So the influence of a bounded function is always upper bounded by its degree. But by influence, I mean summation of all its individual influences. And it's also not that the variance of a function is upper bounded by its total influence. These are some facts that one needs to know some Fourier analysis to see this. This one is, if someone has seen this, this is also known as the Efron-Stein inequality. For this one, you need to know some basic Fourier analysis. But let's assume this for now. So we know that initially the variance of P was at most its total influence, which was at most P. And on expectation, on each branch, the average variance goes down by a significant amount. And as long as the variance of, if the variance of this quantity, this function is also more than epsilon, we make one more query, say we query J, and we move to another sub-restriction. But the point is, if the variance here was high, you again query an inferential coordinate here. So the average variance of the nodes on these two things will be significantly less than the variance here. So as whenever the tree branches, the average variance of the next two nodes is significantly less than the branching node. And then using some simple martingale arguments and loop stopping inequality, one can show that therefore this means the variance goes down pretty quickly. But the key here was as whenever the variance is high, we are guaranteed to find a coordinate with high influence, so that the average variance of the next two nodes is significantly less than the current variance. And that was the key. And to prove that key, we will need to prove the Aaronson-Ambainis conjecture. And so I think my first half is about to end. I'll just state my result. The result we showed in that paper. And so we are able to show the following. Like the title suggests, we are able to show Aaronson-Ambainis conjecture is true for random restrictions. So let's say variance of P. Let's make this assumption because let's even make this assumption. That's fine. So this is our result. If let's assume initially the variance of P is somewhat high, because otherwise you can just start to explain. And let's hit it with a random restriction with survival probability log d by d. And with high probability, this restricted function will have an inferential coordinate. So our final result is that Aaronson-Ambainis conjecture holds for random restrictions. I think I'll stop the first half of my talk here, and I'll give some proof sketches and some sketches of past work on the Aaronson-Ambainis conjecture. Yeah.
Sorry, I don't understand this statement. What is the result? So you're saying we assume that P has large enough variance?
Not too small variance.
Yes, so then there exists a rule?
No. Those are random restriction with survival probability log d by d.
Okay.
You know what?
Suppose this exists, or
over a random choice of row, this holds.
okay, fine. Okay, yes, okay, very good. Take this thing.
What is survival probability?
The
This is
probability
no, wait. So you mean the non-star probability or
the star probability. So most of the things, unfortunately, are getting fixed.
okay.
But still, like on expectation, you have n log d by d many variables, which is still quite large, and you get a poly d inferential coordinate.
So you're now saying that you can do this process that we did before, but you hit it with the random restriction.
Then it works, yeah.
More than-
Yeah, it does not really. You cannot simulate the original polynomial using this.
Okay.
But it's saying it can be considered some evidence of the conjecture being true because it's true for random restrictions.
Okay.
Yeah, we could not show it for all polynomials, but this is some partial progress. And in the next, so I will stop my first lecture here. I think it's been 1 hour. And in the next half, I will do some literature. I'll prove some sketch. I'll give a proof sketch of this result. And while doing so, we'll introduce Boolean functions. We'll go through some literature on past approximation of. We'll go through some past literature about approximating low degree polynomials using DAS and decision trees. I think I'll stop my first half for now. And
So just yeah. So maybe this is a question for the second half, but I'm just trying to get a sense of the intuition, like why Aaronson-Ambainis should be true. But basically, I guess the intuition I have right now is saying, suppose that the polynomial is wild. You know, it has high variance. Then it would be very weird if, like, individually, no coordinate really tips things either way, but somehow collectively it turns out that there's a huge variance. You're saying, no, this can't happen. I mean, if there's a lot of
unless
variance,
you're
then unless you're high degree. So that's where the degree comes in. And do we know? Yeah. So what I was trying to get to is like, is this expected to be like somehow? Is there an upper bound showing you can't hope for better than this? For instance, you just said, does there have to be independence on degree? Yes.
Yeah. So
and you couldn't hope for like some larger function in the variance, or like I just trying to get some kind of feeling for this.
So you need the degree restriction because consider the types function. So this is a degree n, breaking n. This is a degree n function. Its variance is 1/4. That's a large constant. But every coordinate has influence at most log n by n. Okay, you do need the degree in that sense that it's okay. I'm not sure. Yeah, so unless you have a degree restriction, the influences can be as small as log n by n, whereas the variance is constant. But in this case, the degree itself is high, so it does not violate the Aaronson-Ambainis conjecture. So I'll maybe write down the parameters. Is this part of the board visible?
Mm-hmm.
So such functions exist, where the variance is a large constant, but every influence individually is small. So without the additional degree restriction, this other statement cannot hold. Okay, so I hope that answers your question.
Mm-hmm. Mm-hmm.
And the degree of this turns out to be full. So it does not violate the Aaronson-Ambainis conjecture. So yeah, essentially you're saying a polynomial cannot behave that wildly if it's low degree. Like to behave wildly, it has to put mass on its high degree terms. Okay, so does anyone else have any questions? Yeah, all right. So the goal of the second half is to give a proof sketch of this result. And through the way, we'll go through some basic results about approximating bounded Fourier tail functions by Huntas. So let's start. And I'll quickly introduce some analysis of Boolean functions because it will be crucial to the proof. Okay, I just deleted the main reason, but I will restate it again. I hope. So, let me just introduce analysis of Boolean functions in very short. Let's say you have a function. Where's the other one? Oh. Yeah, so let's say you have a function from the Boolean hypercube to radials. And this has a Fourier representation. It can be uniquely represented as a linear combination of the Fourier characters. Where chi is x is the parity of is the product of the coordinates in S. And you can recover f hat s from fx by the Fourier inversion formula. Right. So from this expression, it's clear that the degree of f is the largest S such that the corresponding Fourier coefficient is non-zero. And we can also get nice expressions for variance and influence from this Fourier expression. So let's write down the expression for variance. And this is Parseval's theorem, more or less. We can also write down the expression for the influence of the ith coordinate. That is the total Fourier mass on all sets that contain I. And from this, you can also get a expression for the total influence. Now, the total influence is the summation over I of ith influence. So here, f at s whole square will get counted mod s times. And from this expression, it's clear that two things are clear. First, the ith influence is at most the variance for all I, and the total influence is at most degree times variance, because each of these terms is less than equals to d times f at s square. And these are very immediate from the Fourier expansion. Okay, so, but it's also at least variance of f, and this is also clear. Because in variance, this coefficient is 1, here it's modest, which is at least 1. So these facts are clear. And now I will start by stating a famous result that can be considered as currently the state of the art on the Aaronson-Ambainis conjecture. I'm going to state a slightly weaker version of the theorem so that it seems similar to Aaronson-Ambainis conjecture. Then I will state the actual theorem. So what we have is that Aaronson-Ambainis conjecture is true if you replace 1 by d by 1 by 2 power d. And this so this implies that you can actually simulate quantum query algorithms classically, but you get an exponential blow up. All right, we're going to use this result, and so let's take the full strength of this result, and it says something more. It says that for suppose your Fourier mass above level k is small enough. In that case, you are approximable by your 2 power order k juntas. So let me define one more term first before stating the full result.
So you said before that we know that this is true for constant d and that d logarithmic was like the interesting range. Is this the reason why constant d is already solved?
Exactly. Because if d is constant, 2 power d is also constant. And kind of log n to polylog n is the interesting range where we don't really know anything. And if d is large, like n power 1 by 100, then we know simply by the fact that max inference is 1 by n times variance of f. So kind of like within the range log n to polylog n is the, and I'm going to say a stronger version of this theorem a bit pretty soon, which says why less than log n is not interesting. I'm going to state the full strength of the full version of this theorem in a while, but that will show why even up till log n we don't care. Kind of log n to polylog n is the range where we kind of care. Right. So I'll define some notation. So we call a function L junta if even though they are n coordinates, it's actually a function of some of its L coordinates. And this notation comes from some things like there are things like military juntas where imagine N is the entire population, every population is trying to make some decision. But there are only it's a military junta, so there are only L military leaders, and the decision only depends on what these L guys think. The other opinions are irrelevant. So motivated by that, we call a function L junta if its value depends only on the value of some L coordinates. And we call a function epsilon comma L junta if there is a we call a function epsilon comma L junta if there is some L junta G which approximates f in the L2 norm up to precision epsilon. So, okay, having introduced this notation, let's state this theorem in the full form. So, f is a bounded function and its Fourier mass above level k is very small. So this theorem states that if the Fourier mass of f is a bounded function and the Fourier mass of f above level k is extremely small, then f is actually close to a junta where the number of military dictators is around 2 power order k by epsilon square. And this kind of implies the result about Aaronson-Ambainis conjecture, because let's take k to be the degree of f. In that case, the Fourier mass above level k is exactly 0. So you can plug whatever epsilon you want. So what you get is that your function is very close to a junta that depends only on 2 power order k many coordinates. Now, if the variance of f is high, then one of these 2 power order k coordinates would be influential. And that's how you get Aaronson-Ambainis from this result. Now we are going to use this result and try to prove something. And it will turn out not to work. So we'll try to refine this result. So I'll erase this. So recall what we wanted to show. If we have some function f and we hit it with a random restriction, then that function has an influential coordinate. We'll instead show that it's approximable by juntas. Now, if a function is approximable by juntas and it does not have, and its variance is high enough, then one of the coordinates in that junta will have an influential coordinate. So f is our target function. We want to prove something about f. Let's say the degree is 0, 1. So let's say the degree of f is at most d. And we want to show that random restrictions of f can be approximated by poly d juntas. Because if we can show this, recall that we had assumed initially the variance of f was not too low. So if the random restriction rate is decent enough, with some decent probability, the variance of the restricted function will also remain high. And moreover, with high probability. And moreover, with high probability, this restricted function can be approximated by a poly d junta, which would mean one of the coordinates in that junta will have an influential coordinate. So at first, we're going to try something that will not work out. So let's try to apply the DFKO result. And since we want the number of coordinates to be poly d, we want k to be around log d. Now, one nice thing about random restrictions is that when you hit a function with a random restriction, its Fourier tail decays. So most of its Fourier mass will come pretty low. So if it had no Fourier mass above level d, after a random restriction, it will have no Fourier mass above level PD, where P is the survival rate. It will not have too much Fourier mass above level PD. So if someone has seen the proofs of parity AC0 Fourier tail decay of AC0 circuits by LM, they use this same idea. So let's say we pick P to be the survival probability. Now, initially we had no Fourier mass above level D. Then using some Chernoff bound calculations, we can show that there will be very little Fourier mass above level PD by 100. And we want to set K to be log D. So let's take P to be so if we take P to be log D by 100D and we hit F with a random restriction, the expected Fourier mass above level log t will be small. And what we are hoping is the expected Fourier mass above level log t is small, implies we can apply this theorem and we can get around. And we get that f rho is approximable by a kunta and we are done. But unfortunately, it's not that simple, because if we work out the calculations, you will never get the Fourier mass above level log t to be level k to be small enough. And roughly the reason why this happens is there are some bad things in this expression. So the way you bound the expected Fourier tail above a certain level is you use Chernoff bound. So the bound you get essentially is that given a set of size log t, what's the probability there are more than log t many elements remaining, log t many stars remaining in this set? That gives you the lower bound. So for a k, the upper bound you get here is around e power minus k. Whereas here, you need e power minus k squared. And there's one more bad thing. There's a 1 by epsilon in the exponential. So we would want, for these parameters to go through, we would want epsilon to be around d power some large constant. And then we cannot really get it because these things blows up. And even if we were fine with epsilon being a small constant, this k square would ruin things up for us. So this approach unfortunately does not really work, because although the Fourier tail of a random restriction decays, it does not decay fast enough for us to be able to apply this result. So what do we do? Now, one thing one might hope is maybe this result is not tight. Maybe we can improve this tail bound somewhat. But this same paper constructs an example where this is tight, only this log k is not here. But the log k is a minor value, it does not really change anything. So effectively, this theorem is tight. So what do we do? Now, recall our setting, we have k equals to log t. Now, here's the main observation. We're looking at random restrictions of our low degree function. So this random restriction has two properties. First, its Fourier mass above level k is small. And second, its Fourier mass above level d is entirely zero. So we have two bounds here. We have that at level k it's pretty small. Like at level k we know the Fourier mass is small. But at level d we know the Fourier mass is exactly zero. And this is going to be crucial, because this result only assumes there's very little Fourier mass above level k, but then there could be some Fourier mass above level d. But so our function does not look like this. Our function looks like this. The Fourier tail above level k decays, and by level d the Fourier mass is exactly zero. So now the question is, can we improve this tail bound here, assuming f has degree d? And this is the main result of this paper. Let me write it down. It turns out we indeed can. So this is the main result of this paper. It says that if you additionally assume there's no Fourier mass above level d, you can significantly improve this tail bound. So two good things happen. First of all, there's only a single exponential in k instead of exponential of k square. And the 1 by epsilon came out from the exponential. So now this epsilon is sitting here just as a normal function. And recall our setting of parameters. K was log b, epsilon was b power 10 100 billion. In this case, for this setting of parameters, this is actually exponential of minus order k, which is good enough because Chernoff bound will give you a bound of exponential of minus order k. So to summarize, this is our main result now. This is the key lemma that drives everything else in this paper. We hit the function with a random restriction so that its Fourier mass above level k decays around exponential of minus k. Additionally, we know there is no Fourier mass above level d. So we can use this variant of dfq to show that this restricted function is approximable by a poly junta. Now, since the original function has some variance, with a decent probability, this restricted function will also have high variance. And therefore, one of these junta coordinates will be an inferential coordinate. This way to formalize this using Fourier analysis, but since we are a bit short on time, I'm not doing that. So I think this is the sketch, and for the rest of the talk, I'll give a proof sketch on how to do this. So I'll maybe stop for 2 minutes if anyone has any questions. Or
Maybe just to clarify, the only place you need random restriction is just to make sure that there is decay above level k. Okay.
Yeah,
So you don't need it anywhere else.
no.
Okay.
This is the main result. This is the non-trivial part. If we have an additional degree assumption, you can improve the tail bound.
You said that is almost right. This.
This is also right, but it's not published. Okay, so we'll move on to a proof of this theorem. And how much time do you have remaining? So I'll try to wrap up in 35 minutes. If not, I'll just say, trust me, bro. Because I don't think you will be done in 35 minutes, unfortunately. But I hope I can give a sense of the global picture. Okay, so I'll first give a sketch of how DFK proves their theorem. And their theorem was like broadly speaking, I'll show the final step of their proof. Maybe one of their sub-lemmas. So this was not written explicitly as a lemma in their paper, but if you go through the proof, you will see this is what they prove on the way. So I will write down what they prove. Okay, so we'll prove this. Okay, so let me try to parse this statement. We are giving a function g from the Boolean hypercube to the reals. It's not guaranteed that g is pointwise bounded. We only know that the expectation of g square is at most 1. And suppose g is not a epsilon comma 2 per order k by epsilon unta, then for any bounded function h, the distance between g and h are large. This is what DFQ prove on their way to the main theorem. And let's see how this implies the main theorem. The main theorem says you have f, which is actually bounded everywhere, and its Fourier tail is small. And we want to show that f is approximable by a hunta. So let's assume, for the sake of contradiction, f is not approximable by a hunta. Now we have to, we will use this theorem. So let's take G to be the Fourier truncation of x. So we just look at the Fourier expansion of x, Fourier expansion of f, and just consider only those sets whose size is at most k. And let's take G to be this function. So note that expectation of g square is less than or equal to 1 because Parseval's theorem says the total Fourier mass is 1. So of course the Fourier mass till level k is at most 1.
The statement, yeah, h equals from plus minus 1 to the n to 0, 1.
Yeah.
Like, why can't h be g?
Because g is not bounded.
Okay, so it's not bounded, it's part of the definition.
No, as in
It's a part of the condition.
it's part of the, it's a consequence of the condition.
This implies that G.
Yeah, this implies G cannot be bounded.
If it's not a hunta.
Yeah, they're saying if the expectation of G squared is small
Yes.
and G is not approximable by hunta, then G cannot be bounded.
Okay, I see.
Because for any bound,
Yes, okay.
it's more than that, it's like bounded away from 0, 1 in a large number of points. Because if G was bounded, you could make this error 0.
I see.
But it's like saying G cannot be bounded.
Okay, yeah.
Alright, so let's use this theorem. And let's take G to be the Fourier truncation of f up to level k. This condition is satisfied because of Parseval's theorem. Now we are assuming the Fourier tail of level k is small, but this is exactly the distance between f and g. So if the Fourier tail of f is very small, then f and g are very close to each other. And for the sake of contradiction, we assumed f was not approximable by huntas. This means g is also not approximable by huntas. So g is not a epsilon comma 2 power order k by epsilon square hunta, which means for every bounded function h, the distance between g and h is large. But one bounded function we know is f. So we'll get that g minus f whole square is large. But we just assumed that this distance is small. And that is the contradiction. So I hope this is clear. And now we'll try to follow the same framework. In our case, we have the extra definition, we have the extra condition that the degree of f is at most d. So then we don't need to lower bound the distance from g to all bounded functions. We only need to lower bound the distance of g from bounded degree d functions. So in this lemma, we only need to lower bound the distance from g to degree d bounded functions. And since we don't have to lower bound our distance from all bounded functions anymore, we can expect that we can improve this lower bound. And this is exactly what we do. And now we do the same thing. And essentially the point was that since we are not lower bounding the distance from all bounded functions, we are only lower bounding the distance from bounded low degree functions. We can hope to get a higher distance, and we need to. And I hope everyone is convinced that after this, the same proof gives what I wrote on the left side of the board. So let me try to give a brief proof sketch. How much time do I have? Okay. I don't think I'll be able to finish the proof, but I hope I can set the stones going at least. So yeah, all right. So we have to use something about bounded low degree functions. This is the thing that we are going to use. We're going to use the fact that any such H has low block sensitivity. This is a term that was introduced by Nissan and Szigeti while analyzing. Actually, the first result I said about total Boolean functions being simulatable classically. This notion comes up while analyzing those things. So I'll prove this. I'll mention what this is here. So I'm going to just state this result. So let me try to parse what I'm trying to say. So we have that H is a bounded low degree function. I'm saying, suppose you take any t disjoint subsets of 1 to n, where t can be anything, and you take any input x. Now you flip the coordinates in S1. You get this input and see by how much H has changed in absolute value. You do the same for S2, S3, $.st. And sorry, this is a bad typo. So for each of these subsets, you flip the coordinates in that subset and see how much H changes in absolute value. There's a known result which says that the sum of the magnitudes of all these changes is bounded by order t square. And we're going to use this. So let's see how we use this to show that the distance between G and any such H is lower bounded. So I'll use this part of the board. So here's what we'll do. We will define a distribution that selects L plus 1 distinct points from the L plus 1 points from the Boolean hypercube. So L is some parameter that we will choose wisely to optimize the lower bound. But so we'll define a way to sample these strings from plus minus 1 power n. And we want this sampling procedure to have the following properties. Property 1, the marginal distribution of each of these strings is uniform. Property 2, each Zi differs from X on a disjoint subset. This happens with probability 1. And property 3, so we want that with some probability P, this sum is large. So is everyone convinced that if we can produce these distributions, then we will get that the distance between G and H is large. So it's because note that here in this expression, if you replace G by H, this quantity is always at most order D squared because these sets are disjoint. However, the marginal distribution of X and Z1 are all uniform. So with suppose for the sake of contradiction, G and H are very close together. Then with high probability, G of X will be close to H of X. G of Z1 will be close to H of Z1 and so on. And since the corresponding sum for H is always at most order D squared, with very high probability, this sum will also be at most order D squared plus N. But you are getting that with at least some P probability, this sum is at least D cube. So that is the contradiction. And okay. And let's give a sketch on how to produce these sets X, Z1 to ZL. And I don't think I'll be able to go on the full detail of the construction, but let me try to think what parts I should omit and what parts I should keep. So please give me 1 minute. Okay, let's see. So I erase this because I will need this blackboard, but recall the conditions. Expectation of G square is at most 1 and G is not approximable by quintus. So under these assumptions, we have this set M. So we'll show that under these assumptions that we made, we'll be able to partition this set N into 2 parts. Let's call this A and let's call this B. It is a bit larger. Okay. Now we define how to sample X. Recall that we want the marginal distribution of X to be uniform. So we just pick X uniformly at random. Next. So let's say we pick X, let's say this is the set U and this is the set N minus U. So X is chosen uniformly at random. So let's denote the 2 components of X as A and B. So A is the coordinates in U and B are the coordinates in N minus U. Okay. So, and okay, we have chosen X is done. Now we have to choose Z1, Z2, dot, ZL. And the way I will do this is, I will look at A. Now, depending on A, I will choose some of these subsets, S1, S2. So I will choose this. Depending on A, I look what A does, and then I'll select L mutually disjoint subsets, and I'll choose a value of a noise operator rho. Now I'll define how you sample Zi. So Z1 is sampled as follows. So Z1, the A part will be same, and the B part will be replaced by B1, where B1 is defined by as follows. So we do the following. Let's say these are S1, S2, SL. Usually S1, S2, SL, they depend on A. But anyway, you look at A, then we create this partition, not partition, some part might be remaining. We take these disjoint subsets of B. Now to sample Z1, we keep A the same. Outside S1, we keep B the same as well. Now within S1, we flip each coordinate of B with probability 1 plus rho by 2. So this gives us Z1. And we similarly get Z2 ZL. And this property is clear because Z1 differs from X only on S1. Similarly, Z2 differs from X only on S2. And by the way we chose them, S1, S2, SL are just disjoint. So property 2 is taken care of. Property 1 is also easy to see because the A part is uniform, and conditioned on A, the B1 is also uniform because it's this bit is like you first select a random bit, then add a noise operator, which is the same as selecting a random bit. So properties 1 and 2 are taken care of. We need to take care of property 3. So that way we need to select these subsets wisely so that property 3 holds. I think I'm running out of time now. So how much time should I?
You should have at least 10 minutes.
10 minutes, but yeah, that's what I meant by running out of time. Sorry.
You ask me how much time I have.
Yeah. I mean, let me see. So, okay, so what for now, what's clear is that no matter how we choose these disjoint subsets S1 to SL, properties 1 and 2 are taken care of. And we only need to take care of property 3. And for that, we need to carefully choose the S1 to SLs. So let's say how to do this. And crucially, S1 to SL will depend only on the choice of A. So we look at A, and we have to choose S1 to SL. Now, some A's we call good, some A's we call bad. Good and bad is a definition that we'll define in the paper. I'm going to skip it for now, and just trust me that if A is good, then something good happens. So we define good in such a way that probability A is good is at least P tilde. This part actually mimics the proof of DFQ up till a certain point, because not that, this part just follows DFQ with very minor modifications, maybe even those are not needed. So we define some notion of good. This is not done explicitly in the DFQ paper, but if you read their paper carefully, you will see essentially they try to do something similar. So anyway, we define some of these possible A's as good and some of these possible A's as bad. And we say that at least the P tilde fraction of A's are good. Now, what we do is if A is bad, then we don't care what S1 to SL are, we just randomly choose them. We really don't care because those will not contribute to this probability. We only care what happens when A is good, because now we have a chance of choosing good S1 to SL. Now, what we essentially show is that if A is good, then there is always a choice of S1 to SL, such that this holds conditioned on saying A. So, whenever this first part is good, the probability is at least P, as mentioned above. And if the first part is not good, we don't care. Just leave it. So if you show that the probability of A is good is P tilde, then conditioned on this A, this will be big with some probability. And so we will define what good is. We'll show that under the assumptions with some probability A is good. And then we'll show that for every good A, there is a way to select S1 to SL wisely, such that this third property holds. So I'll define the definition of good. And now it's going to get a bit technical. I mean, it already has, but it is still going to. Yeah, anyway, let's see. So, the definition of good. So, you look at the restricted function. Sorry, this was easy. So, we look at these restricted functions and we classify coordinates according to heavy or light. Now, we call a coordinate in I heavy if the Fourier coefficient of I in this restricted function is large. Otherwise, we call it light. So we classify the coordinates according to whether they are light or heavy. And the condition we want for A being good is that the total mass of the light coordinates is still very large. So this is our condition for being good. To recap, after seeing A, we find what the light and the heavy coordinates are. The light coordinates are the ones whose Fourier coefficient is smaller than the threshold. And the condition is that the total weight of these light coordinates is still pretty large. And now I have to define how to select. So essentially, this linear form looks smooth in the sense all these coefficients are very small, but still their total magnitude is pretty high. This will be Gaussian. So now I have to define the partition S1 to SL. So let's do that. And I'll draw this picture again. So this is B and this is A. Now suppose we chose A. And suppose A is good. Then the total magnitude of the light coordinates is very large. So let's say this is light, this is the light part, and this is the heavy part. Now in the light part, this total sum is large, but each sum individually is very small. So you'll be able to greedily find a partition where all this, let's say we will partition this into L partitions. Where each partition will get total mass at least mu by 2L. We can do this as long as theta is small enough compared to L. Like intuitively speaking, what's happening is that like here each of this summation in total is very large. but each summand individually is very small. So if you pick L appropriately, you'll be able to find a partition such that each partition gets a large amount of mass, where the number of parts depends on mu and theta. So, but the point is, if you pick L appropriately, you'll be able to find a partition of the light coordinates so that each partition gets total mass at least mu by 2L. And I think the time to hand off has started. And I will just do what I promised. I will say, trust me, bro. If you look at the proof of DFKO and apply a noise operator only to this restriction, you follow the proof of PFKO and things will work out. So I think explaining this whole thing will take a lot more time. So as I promised earlier, I will say, trust me, bro, it works out. So that's the proof. So any questions?
Why is defining distribution the natural way for this?
I initially proved it in a different way, but this turns out easier for exposition.
Okay.
I mean, effectively, that way is equivalent to this way. So, kind of. We just have to use the fact that the function has low block sensitivity somehow. So, you have to use this content. You have to use that for if you replace g by h, this function is always small. We have to use that. So, you have to find lots of disjoint points where they differ.
Does that other way we talk about block sensitivity?
No, it does not. So, they don't have the low degree assumption. They only have the bounded Fourier field assumption.